my name is Nate. You can call me a shader artist, designer. So I make real-time shaders for the web. So shaders are everywhere. You probably have seen them. They're in all the games, movies, animations, and websites. So shaders can greatly enhance the entertainment experience and really engage you in what you're seeing. So a few years ago, I created shaderdaily.com, and I've been playing around with shaders, exploring different topics in graphics programming. Today, my goal is to give you a brief overview of shaders and show you an example you can play with. OK. So shaders are programs that tell a set of pixels what color they should be at a certain time. So all the pixels can be any color as a result of mixing red, green, and blue channels. So these channels can be controlled using various kinds of algorithms to create a wide range of effects. And a vital part of this puzzle is the GPU. Like the GPU allows us to instruct millions of pixels simultaneously. And this enables us to create real-time graphics. All right, so a shader has two programmable parts, the vertex shader and the fragment shader. The vertex shader transforms the position of the vertices. Then triangles are made. The pixels inside the triangles are selected to be shaded. So these selected pixels or fragments are sent to the fragment shader. The fragment shader uses mathematical algorithms to color them appropriately, and the final result is displayed. There are different kinds of shading programming languages. Each one is designed to target a specific graphics API. The one I use is called GLSL, and it targets the OpenGL graphics API. And GLSL is widely used for web-based graphics through WebGL, which is how I use it. So all my shaders are like on the web. GLSL looks a lot like C with built-in vector, matrix, and sampler types, and it comes with a great math library. And unlike C, it doesn't have any pointers, recursion, or dynamic memory allocation. We did learn about a programming language yesterday that doesn't have pointers or dynamic allocation. COBOL? Yeah, cool. All right, so you can go to this website. And if you have your laptops or smartphones, you'll go to this. It's code-shaders.versal.app for the remainder of the talk if you want to follow along. So this website is made using Three.js, and it uses WebGL underneath. And also CodeMirror, which allows us to edit the GLSL code in real time. We're going to be creating this effect in 3 steps. So it's like a classic tunnel effect. All right, we're going to use the circle sign distance functions to draw the circle. And then we're going to turn the circle into a grid of circles. And then finally, we're going to turn this grid of circles into this tunnel shape over here. So in shaders, we use sign distance functions to draw different kinds of shapes. These sign distance functions, they take the x and y position of each pixel, and they do some calculations, and they return a value for each pixel. So, all right, they return a value for each pixel. So if our pixel, typically what happens is if our pixel has a value of 0 or less, it's going to be inside our shape. If it is outside our shape, it's going to have a positive value. So for this circle sign distance functions, what we need to do is use the Pythagorean theorem right there to find the distance. And from this distance, we're going to subtract the value of our radius, and that will give us a sign distance field for our circle. So, so this stores our position of our pixels in a coordinate system. And our color has a vector 3 value for red, green, and blue. So our circle sign distance function, it takes the x and y position of each pixel. It calculates the distance from the center using that Pythagorean theorem, but there's a built-in length function that we can use for that. And then it subtracts the radius. And this will give us our circle sign distance field. So if our pixel within the sign distance field has a value of 0 or less, we're going to color it green. And if it is greater than 0, we're going to color it black. And that's how we draw our circle. Now we're going to turn our circle into a grid of a grid of circles. And we do that using two simple steps. First, we're going to multiply our coordinate system by our grid size. And so if we want a grid of 10 by 10 grids, we're going to multiply by 10. And second, we're going to drop the whole number values and keep only the fractions. And this will make the values go between 0 and 0.9 in both the x and y directions for each grid. So we're going to be using this convert to grid function, which takes our coordinate system and then first multiplies by the grid size and then takes the fractional part. And so we're going to generate the sign distance field inside each of these grids. And so again, we're going to test out, where our pixel, what our pixel value is. If it's less than 0, we're going to color it green. And if it is greater than 0, we're going to color it black. And the very last thing that we'll do is turn that coordinate system, this grid of coordinates, this grid of circles into a tunnel. And up to this point, we've been working with a Cartesian coordinate system of x and y values. So in order to draw our tunnel, we need to convert from a Cartesian coordinate system to a polar coordinate system. So a polar coordinate system describes each point as the distance from the center and angle. So we find the distance just like using the Pythagorean theorem for the circle sine distance function. And for our angle, we're going to use the arctangent of the opposite value over the adjacent. So the y value over the x value. And that's how we get our angle value. So instead of using the x and y values for the Cartesian coordinate system, we can map all of the pixels into a polar coordinate system by using the radius as the x and the angle as the y value. So in the code, I'll show you, we're using this two polar chords function, which uses this built-in length function to calculate the radius value, which is basically the Pythagorean theorem value for that for the distance. And then we're going to find the angle using this built-in arctangent function, which takes in the y value and the x value. And then we're going to assemble our polar coordinates by taking the inverse of the radius to pinch it together and then adding time for animation and then reducing the angle. And to use it, first we're going to convert our Cartesian coordinate system into a polar coordinate system. And then we're going to convert our polar coordinate system into a grids. And then finally, we're going to draw circles inside each grid. And that's how you get this tunnel shape. And the very last thing that I want to show you is how to hide this distortion in the middle. And this happens when multiple small things are drawn so close together. It creates this distortion effect. And we can hide that by drawing yet another circle that fades out like a radial gradient. And that's that part right there. And the code for that one is right at the bottom. And the circle mask. So we're mixing the color black with our previous distorted color. And what's happening is if our pixel value is 0, it's going to be black. If it is 0.45, it's going to be the previous color. So everything in between is going to be a smooth gradient between those two colors. And that's basically it. So shaders are, you can use them to make any type of effect that you want to make. Whether you're making something for an artistic purpose or whether you're creating a specific effect for a client, they're a versatile tool to have in your toolbox. And that's it. Thank you. You can find me on here. Talk to me about shaders whenever you want. Thank you.